Well, good afternoon. Welcome to NASA headquarters in Washington. My name is Dwayne Brown with the Office of Communications. Today's briefing will preview the Dawn spacecraft's upcoming year-long visit to the large asteroid Vesta. We'll have presentations, then we'll open it up for questions. And just a quick reminder that all of the images and information you will see today are on the web at www.nasa.gov/dawn. Before we get started, let me introduce you to today's speakers. First up will be Jim Adams, Deputy Director, Planetary Science Division, NASA headquarters. Bob Mase, Dawn Project Manager, Jet Propulsion Laboratory, Pasadena, California. Chris Russell, Dawn Principal Investigator, UCLA. And Carol Raymond, the Dawn Deputy Principal Investigator, also from JPL. So with that, I'll turn it over to Jim.
Thanks, Dwayne. It's been an incredible year for planetary science. We started the year off with 2 cometary encounters and then inserted the MESSENGER probe around the planet Mercury. And today we're happy to tell everybody about the opportunity to insert the Dawn mission into orbit around the asteroid Vesta, one of the largest objects in our asteroid belt. The Dawn Science Campaign at Vesta will unveil a mysterious world, an object that can tell us much about the earliest formation of the planets and the solar system. Indeed, the science community is very excited about that opportunity, and to study this particular asteroid up close and personal is a very unique opportunity. Dawn's journey to Vesta started back in 2007, and since then it's been steadily thrusting its way past Mars and out into the asteroid belt, where it's slowly catching up with the asteroid. This system has enabled us to not only visit Vesta, but when we're done there, we'll move on to the dwarf planet Ceres. The way we can do that is through an ion propulsion system that Bob is going to tell us more about in a few minutes. Just as unique as the Dawn spacecraft is its team. The Dawn team is going to, over the next year, enable us to get a bird's eye view of this new world. And until now, it's only been a fuzzy blob. But Chris and Carol have more to show us about the science of the asteroid Vesta and why it's important. And plus, I believe they're going to have a sneak peek at some of the earliest images. Some of us recall with amazement seeing those first images from the Mariner series of Mars. And I like to think that this week, next week, and over the coming year, that's the kind of excitement that we're going to see as we unveil this new world. I think that it's a fantastic opportunity for young and old alike to get a sense of just how vast and unique our solar system is. Over the next year, the Dawn team will paint a face on that fuzzy blob. The pictures will just get better and better, and we'll begin to understand this awesome new world. And with that, I'll give you Bob.
All right, well, thank you, Jim. After traveling for nearly 4 years, 1.7 billion miles, and 2 laps around the sun, Dawn is finally on our final approach to Vesta. Today, we're only about 96,000 miles away. That's about a third of the distance from the Earth to the Moon. Our destination is within sight, and this team is very excited that we're finally closing in on Vesta. And I'm very pleased to be here today to tell you a little bit about the Dawn mission and about the background on how we got here. If we could roll the first video, you'll see some spectacular footage of the Delta II launch vehicle that started Dawn off on this amazing journey back in September of 2007. And as you watch that, I'll tell you that the Dawn mission is unique in that we're going to be the first mission to rendezvous with not just one body, but 2 solar system bodies. Many spacecraft have flown by multiple bodies, but Dawn will be the first to make an extended port of call at our 2 destinations, Vesta and Ceres. These are 2 of the last unexplored worlds in our inner solar system, and these are large bodies that reside in the asteroid belt between Mars and Jupiter. So if we go ahead and roll the second video, I'll describe how do we get there. Vesta and Ceres, like the planets, are in orbit around the Sun. So to get to Vesta, Dawn is placed into orbit around the Sun, and over a period of months and years, we shape its orbit to match Vesta's orbit. We do this with the ion propulsion system, which is represented by the blue glow that you can see in the video. After launch, we flew by Mars for a gravity assist in 2009, and we completed almost 2 full orbits around the Sun. We'll rendezvous on July the 16th and be captured into orbit around Vesta. We'll orbit Vesta for a year before starting our climb out to Ceres, and then we'll arrive in Ceres in early 2015. Now, to get to these two bodies is no small feat. They're relatively far away from the Sun, 2 to 3 times farther than the Earth, and solar energy, which powers the spacecraft, is pretty scarce at those distances as well, 4 to 9 times less than here on the Earth. So to capture enough energy, Dawn has 2 very large solar arrays. Each is 27 feet in length. That's about the width of a singles tennis court. And tip to tip, the total wingspan is about 65 feet. That's the distance from the pitcher's mound to home plate on a professional baseball field. This makes Dawn the largest interplanetary spacecraft that NASA has ever launched. And our journey is made possible by ion propulsion. This advanced sounding technology has actually been around in concept for decades. You may have even heard it on the original Star Trek TV series or in the Star Wars movies. You'll recognize the TIE fighters, the twin ion engines. They're impressive ships, but we do them one better on Dawn. We actually have 3 ion engines on the spacecraft. Now, these ion engines are very efficient in the sense that they require very little propellant mass compared to conventional chemical systems. Xenon gas is used as the propellant, and it's ionized by large electric fields, and these ions are accelerated at very high velocities out of the thrusters. Now, this requires a tremendous amount of energy, up to 2,500 watts of power, which is another reason that the Dawn solar arrays are so large. Now, conventional chemical systems can generate tremendous amounts of thrust and acceleration. To use a terrestrial analogy, they go from 0 to 60 in just a few seconds. Ion engines, on the other hand, produce very low thrust, about as much as a single piece of paper would push down on your hand. So this means we go from 0 to 60 in about 4 days. But the ion engine can continue to thrust and accelerate day after day, month after month, eventually achieving tremendous velocities over time. So with less than 1,000 pounds of xenon on board, over the course of our 8-year mission, the ion propulsion system will provide more than 24,000 miles per hour of velocity change. To put that in context, that's about the same we got from the Delta II launch vehicle that lifted Dawn off of the Earth. So this is truly an innovative technology that enables us to do things and go places that would otherwise be either very expensive or downright impossible to do. So now, after nearly 4 years of travel, we've matched Vesta's orbit around the Sun, and like 2 cars traveling together at high speed down the freeway, relative to each other, they appear to be moving very slowly. And as Dawn and Vesta are traveling at tens of thousands of miles per hour around the Sun, Dawn is closing in on Vesta at a modest 260 miles per hour. So as we roll the last video showing the approach to Vesta, I'll tell you a little bit about the team that makes this all happen. Our principal investigator, Dr. Russell at UCLA, leads our mission. Project management and the flight operations are performed at NASA's Jet Propulsion Laboratory. The spacecraft was designed and built by the Orbital Sciences Corporation, our capable partners just down the road in Dulles, Virginia. We have 3 scientific instruments on Dawn, and I'd like to take this opportunity to recognize and thank the German Aerospace Agency and the Max Planck Institute for Solar System Research for providing and operating the framing camera, which is going to show you some of the images you're going to see in just a few minutes. Also, the Italian Space Agency and the Italian National Institute for Astrophysics for providing and operating the visible and infrared mapping spectrometer. And our third instrument, the gamma ray and neutron detector, was built by the Los Alamos National Labs and is now operated by the Planetary Sciences Institute. So in addition to our instrument partners, our PI has assembled a first-rate team of scientists and investigators from around the country and around the globe. In this regard, Dawn is truly a shining example of a successful international collaboration. And of course, no flight operations would be possible without the tireless and dedicated support of the Deep Space Network. So today, Dawn is halfway through our 3-month Vesta approach phase. We'll capture into orbit in mid-July and spend the next several weeks slowly spiraling into our first science orbit. Then we will begin the science campaign in the 2nd week of August. We've already begun to image our destination, and the team is very excited that our destination is finally within sight. The image of Vesta is slowly coming into view, and I'll now hand you over to Dr. Russell to explain the significance of this unknown world that we're about to explore.
Thank you very much, Bob. As Dawn Principal Investigator, it's my job to make sure that the mission achieves its scientific objectives. And I will start doing that in earnest very shortly. But right now, all we're doing is taking navigation images. And so they're not the scientific product that we will get, but they're very interesting, and I'd like to share them with you today. To get these images, the spacecraft's thrusting, and it's not pointing at Vesta, so it has to turn off the thrusters, turn around and look at Vesta, take the data, and then return it to Earth. So we only do this about once a week, at least at the start. We're picking up the speed now and taking them every twice a week. But these images, when we're staring at Vesta, we take the order of, say, 30 once a minute, that order. And then since Vesta spins at a degree a minute, we're seeing about 30 degrees in these first few frames. And then later we'll see about an hour's worth of images and see it rotate about 60 degrees. Could we have the first video, please? So the first image was taken in May, May the 3rd. And at that time, we were about 4 times the distance of the Earth to the Moon. Now we've got much closer, and we are now about half the distance between the Earth and the Moon. As we take a look at these images, we can see features rotating. We don't know exactly what they are. Many of them look like craters, but we're waiting till we get higher resolution to make interpretations of what we see. Whatever is on that surface, it's a lot more varied and than we would have thought from the earlier Hubble pictures. Now, Vesta is no stranger to people on the Earth because Vesta has been visiting the Earth through a set of meteorites that have fallen to Earth over the Earth's history. And at the present time, about 1 meteorite out of every 20 that falls to Earth comes from Vesta. And here is an example. This one fell in Australia, and we've sliced it to show the interior of the meteorite. You can go to a store and buy this material. It's that common. It's not like the lunar samples. We have more Vesta samples than we have of the Moon or Moon and Mars. One of the reasons we're going to Vesta is not only because it's so big, but it's also one of the earliest bodies to form in the solar system. So the surface of Vesta will hold a record of the earliest history of the solar system. Another important thing is that our understanding of the history of the solar system tells us that these bodies were on their way to becoming larger bodies. We think of Vesta as a protoplanet. It would have grown into a planet had it been allowed to continue. But the formation of Jupiter started stirring up that region of the asteroid belt and preventing materials from coming together any longer. In fact, things started bumping into one another and breaking up. So we think that Vesta is a good example of those early formation, the bodies that were forming early in the solar system. However, it's just an example of what was around, and there were other bodies that came together in the inner part of the solar system. They grew larger, they formed Mars, they formed the Earth, and so bodies like Vesta are building blocks. We believe that these were examples of the building blocks. So we're going back and doing some sort of investigation in our roots, the roots of the solar system. Could I have the next video, please? This shows an basically an artist's conception, an animation of Dawn flying over the surface of Vesta. And what you see there are craters, and craters are very important to us on this mission because they excavate beneath the surface. Our instruments only sense what's on the surface. They're not sensing very deeply, only about 1 meter into the surface at most. So these craters are very useful for probing deeper down into the body. Now I'd like to hand over the mic to Dr. Carol Raymond. Dr. Carol Raymond is the Dawn Deputy Principal Investigator, and in that role she's been doing most of the scientific planning, and she'll tell us more about what Dawn is going to do. Carol.
Thank you, Chris. So as Chris said, I'm going to talk to you about how we're going to explore Vesta over the next year. This is an unprecedented opportunity to spend a year at a body that we really know nothing about. We're going to do a very comprehensive job of mapping it. We'll be mapping the mineral composition of the surface, and in particular investigating the link between Vesta and this class of meteorites, which we have in hand on the Earth. We're particularly interested in a large feature at the south pole of Vesta, a large crater, because we expect it resulted from an impact which was large enough to have blown away the crust and exposed the deep interior of Vesta. So we're going to be able to peer into Vesta by observing within this crater. We'll be imaging to define the surface features of Vesta at both large and small scales, and using them to define geologic units based on their colors and textures. And we'll be looking at individual lava flows and craters on the surface down to scales of tens of meters. So we're really going to get to know the surface of Vesta and decipher its geologic history. At a much coarser scale, we're going to be looking at the abundances of the elements on the surface. And this, together with the mineral composition data, is going to enable us to understand more about the formation of Vesta, the process by which it resolved into different layers, and what the impact of initial conditions was on Vesta's evolution. And then finally, we'll be mapping the gravity field of Vesta to understand the internal layering and confirm the presence of a metallic core. So I'll explain a little bit more then about what the instruments are on Dawn and how we're using them. We have 2 identical framing cameras from the Max Planck Institute in Germany. We use them one at a time and map the surface in 7 color filters, whereas most of the images are in the clear or panchromatic filter. We image looking directly down at Vesta, as well as taking data from multiple angles so that we can use the shadows to develop the heights of the surface using stereo processing. These image mosaics reveal the information about the craters, and together with the mineral composition data, produce geologic maps. We carry a visible and infrared spectrometer, which measures the spectrum of reflected light from the surface in the UV to IR range, and this gives us diagnostic information about the minerals so that we can, together with the camera, develop these geologic mosaics and then decipher the processes which have been occurring on the surface to produce what we're seeing today. In the next slide, it's coming up, we see 2 views of Vesta in reflected light, in single bands of visible light and infrared light. And these images were taken from the visible infrared spectrometer provided by the Italian National Institute of Astrophysics. And they were taken mainly for calibration purposes, so they're very, not very well resolved and much lower resolution than the framing camera images you just saw. But even at this resolution, at 200,000 miles from Vesta, we can see some differences in the reflectance of Vesta between these 2 wavelengths. In the next animation, we'll be looking at a simulation of Dawn being captured by Vesta. And as we spiral in on approach using the ion propulsion system, we capture and then continue to thrust to achieve our first dedicated science orbit, which is the survey orbit at about 2,700 kilometers. There we turn to Vesta. We spend about 20 days in 7 orbits, making low-resolution maps with the visible infrared spectrometer and taking limb, mosaic, and direct images of the surface with the cameras. We then spend about 28 days thrusting into our high-altitude mapping orbit, where we are spending 30 days making 6 complete global mosaics of the surface in the clear filter and in color filters and at multiple angles to do the height mapping. We also take high-resolution spectrometer data, mainly of the southern hemisphere, which is well lit at the time of this orbit. We subsequently spend another 39 days spiraling with the ion propulsion system down to the lowest altitude orbit, which is only about 200 kilometers above the surface. And there we have enough sensitivity to measure gamma ray signatures of the individual elements, and also to to be sensitive to the perturbations of the gravity field and map the gravity of the body. After spending our 70 days in the low altitude orbit, we spiral back out and stop again at the high altitude orbit to map the terrain which has become newly illuminated as the sun has moved north relative to Vesta. So we complete our height mapping in that orbit, and then we will continue to spiral out until we've escaped from Vesta, and on we go to Ceres. So while we take data, all types of data in each orbit is optimized for a particular objective. And as I mentioned in survey, the field of view of the spectrometer is large enough that we can make a global mapping of the surface. So that's our primary objective in that orbit. And we do this with the sun almost directly behind us, which is optimum for measuring the reflected light from the surface. As we go lower and lower in orbit, the sun angle increases, which is better for taking the framing camera data because we'd like to see shadows to be able to look at the topography. So as we go lower, we still obtain higher and higher resolution spectrometer data, but it's not as complete or as high sensitivity as above. When we designed our low altitude orbit mapping orbit to be able to resolve the individual elements and the ratios of those elements, which tell us about the chemical evolution of the surface of Vesta, and enough resolution in the gravity field to be able to understand the internal structure. In the next animation, we see in a notional sense the spacecraft in its high altitude mapping orbit. Vesta is rotating at about 5.3 hours, and this is a 12-hour orbit. So we see coming down the lit side of Vesta, taking the framing camera images, which are the blue squares, and we also see that co-located with the framing camera images is the green slit, which is the Vera spectrometer. When the spacecraft's on the dark side of Vesta, it's turning to Earth, and it's sending those data back before it comes around and starts again. We do take these images constantly in swaths as the body rotates under us, and in that manner we build up complete coverage of the surface over 10 orbits. And then we do this 6 times. So I'd like to return then to the last rotation movie we took of Vesta on June 20th and talk a little bit about why anybody should care about the Dawn mission. In this animation, we compare the data from Hubble Space Telescope to the latest data from Dawn. They're rotating in the same manner. And what we see is the intriguing patterns of bright and dark and the ellipsoidal shape of Vesta resolved by the Hubble Space Telescope has now resolved into a very complex pattern of brightness variations on the surface of Vesta and intriguing suggestions of topography, making it obvious why it was really worth getting to this body. Once we fully map the chemical nature of the Vesta surface and understand its relationship to the meteorites, write its geologic history, understand its topography and its gravity field, we're going to begin to understand the role of Vesta's size, the timing of its formation, and its bombardment history in creating the protoplanet that we see today. And this protoplanet, as Chris said, is literally a building block of the terrestrial planets. This will give us better tools to understand the thousands of fragments that are out there in the asteroid belt, and understand better then how they contributed to shaping our planetary neighborhood. So in the course of preparing all the science observation plans for Dawn, it's become clear that this tiny world has huge importance. Vesta is a window into the early origins of our solar system and the terrestrial planets. And as we explore Vesta, we take a virtual journey back in time to the beginning of the solar system. We're all extremely excited. We're literally on the edge of our seats, waiting for this data to come in, and we would like you all to come on the journey with us. Thank you.
Thank you, Carol. Okay, so we're going to now transition into questions. And before we go to the phone bridge, I would like to remind our audience out there that all of the information is on the web at www.nasa.gov/Dawn. Let's go to the LA Times. Tom.
When you say 1 in 20 of the meteorites that reach Earth come from Vesta, I mean, can you explain that? Are these the rubble that surrounds it in orbit, or are they being knocked off Vesta, or what do you mean precisely?
That if you take a look at the pictures we just showed, you'll see that the surface is heavily cratered, or appears to be, and it's very irregular. So over the years, much material has been knocked off the body and is floating between us and the Earth, or the Earth and Vesta. And it gets into gravitational resonances with Jupiter and gets scattered towards the Earth. And so there's this constant stream, almost like a highway of material, from the neighborhood of Vesta, the stuff that was knocked off perhaps originally 4 billion years ago, but maybe some only 1 billion, some maybe just 1 million years ago. And that makes its way to the Earth and falls through the atmosphere, and we pick it up on the surface of the Earth. Now, having said that these are from Vesta, all I can say is that this material has the same reflectivity as Vesta, the same sort of inferred composition as we'd expect from Vesta. It looks like it was formed on the surface of a body about the size of Vesta, and the material that comes down to Earth shows the evidence of heavy bombardment. So we put all that information together, and we believe that the original source, the ultimate source of this material, was Vesta itself.
Okay, our next caller is Pete Spots from the Christian Science Monitor. Pete, are you there?
Yeah, can you hear me?
Go ahead.
Hello?
We can hear you.
Yeah, the question I have is, oh, good, okay, thanks. Yeah, I was wondering, you were sort of getting to it when you were showing the Hubble images, but I wonder, with the support you may have been getting over the last couple of years from Hubble and from ground-based observatories, I wonder if there are any examples of sort of specific observations that have tended to whet your folks' appetite for this, understanding the excitement level already is pretty high.
Well, we have in the audience here with us John Young Lee, who was one of those who took the Hubble, the most recent Hubble pictures. And so if, as a typical excited observer, let's ask John Young what has whetted his appetite.
previously, Hubble has given us a lot of support to observe Vesta and in the mission. And there were totally 4 HST Hubble Space Telescope observations of Vesta. And we use those images to map Vesta's northern hemisphere, southern hemisphere, and also to infer the shape of Vesta. And most recently, we use Hubble images to improve the pole orientation of Vesta. And that has given a lot of help in the trajectory design and long-term planning. But the limit of Hubble is that it is near the Earth and is very far from Vesta, so the spatial resolution is very, very low. And that's why we still need Dawn to go there and get us a lot more information about Vesta.
Okay.
Thank you.
Well, actually, I have a question that's come in. We have a lot of media watching this, and also some museums. And the question is from one of the .coms that talk about careers, and scientists and engineers, when they get together, exciting things happen. So they would like a question on, for each of you, what inspired you all to go in your respective careers? Jim, you want to start that?
That's too long a story, Dwayne. Actually, my father was in the aerospace industry and worked on the Apollo LEM and encouraged me to pursue my talents in science and math. And so I went to college and I got a degree in physics and found that I liked it. And over time, ended up back in the aerospace industry, just like my dad.
Bob?
Okay. Well, I grew up in Florida, which was not too far from the Kennedy Space Center, so I could actually watch the space shuttle as it was launched. And so that, in addition to an interest in science and engineering, led me to a degree in aerospace engineering at Purdue University, and of course that led me to the Jet Propulsion Laboratory.
Chris?
Well, when I was in high school, I took an aptitude test, and the guidance counselor came up to me and said, you should be an engineer. And I said, engineer, maybe, I'd rather do science, okay? So I started, taking courses that prepared me for doing scientific research. And when I got my bachelor's degree, I really didn't know exactly. I mean, there's a lot of boring things you can do in physics, and I had prepared myself well in physics, but choosing between these various things was a little bit difficult. But I took a summer job in which I worked on satellite data. We were taking observations basically of the sun using measurements in the Earth's ionosphere. I liked that. Of course, then the summer was over, and that's the problem with summer vacations. You have to then hit back into the real world. And so I went into a physics department and started to do some of these things that large teams of 200 physicists do. I said, maybe there's some space physics around here. So I went around the university and talked to people, and I found a group that was working in space. I said, do you have room for another person? And they said yes, and that started me off. And I just have been lucky ever since of being able to get into exciting projects and go to one stage of exploration to another, and I've been very, very lucky in my career.
Carol?
Yeah, I always loved science in school, and I studied geology and physics, got a degree in both, and then went on to grad school. And while I was getting my degree at Columbia University, I was studying the floor of the ocean and how the interior of the Earth convected, and various things about the dynamics in the interior of the Earth. But during that time was a time when Earth observation from space was becoming more and more common. And I started to pull in satellite data sets to get a different view of things. And before I knew it, I was working at the Jet Propulsion Lab, trying to help with getting gravity and magnetic field satellites launched around the Earth. But a geophysicist on the Earth is no different than a planetary scientist at Mars, pretty much interested in the same things. And the data from the Mars Global Surveyor began to come in and opened a whole new view into Mars's history, which then just became incredibly interesting. So at that point, I really started to invest most of my time into planetary scientists and the evolution of terrestrial bodies, of which Vesta is one. We call it the smallest terrestrial planet. And it's very, a lot of the things that are going on there are not that much different than what happens on the Earth. But I'll also say that I think what really drove me a lot in my career was the desire to explore, to always go to new places, to see new things. I've done a lot of research in Antarctica. I've sailed on ships surveying the ocean. And taking this virtual journey is very similar in terms of the excitement level and just the wonderful feeling of achievement you get when you've done something really interesting. So,
Thank you all. Let's take at least another call from our phone line. Let's go to Mike Wall from space.com. Mike, are you there?
Yeah, sure. Can you guys hear me?
Go ahead, Mike. Yes.
Yeah, I was just hoping that you guys could actually talk a little bit about what it's going to be like to be captured by this object's gravity. Are you concerned at all? I mean, is this going to be a very complicated maneuver or a tricky one because it's a relatively small body? It doesn't have all that much gravity. I mean, is this like a very complicated maneuver that you're going to be doing to actually to go into orbit around Vesta?
Okay, I'll go ahead and take that one. It turns out that this is a different type of encounter than we're used to with most of either the planetary types of encounters that you've seen that have the critical orbit insertion burns, and it's also different than the small body flybys that we've seen on some of the recent missions as well. Vesta is not a tiny small body like Temple or Hartley or any of those, which are only just a few kilometers, very small, traveling at very high speeds. Vesta is large, has 500 kilometers across. It has a small but a significant amount of gravity. And so being captured by Vesta's gravity is not a problem, it's not challenging. We're also different because we're using our ion propulsion system to capture into orbit around Vesta, as opposed to more conventional missions that use a chemical system where they have a specific burn that has to happen at a very specific time. With the ion propulsion system, again, we're just shaping our orbit to gently pace Vesta's orbit around the sun. And so at that point, we really just slowly rendezvous with Vesta and slowly capture into orbit around it. And it's a very slow, smooth, gradual process that happens very gently on this mission, as opposed to some of the more conventional missions that we've seen in the past.
Okay, we're going to go ahead and wrap it up. I want to thank you all for joining us. Congratulations to the Dawn team. And again, visit www.nasa.gov/Dawn. Science never sleeps.